All right, we are going to continue our discussion on kinematic equations in terms of rotation. So we are now going to start with this formula, omega equals d theta dt. And we're going to do something similar to what we just did. So we're going to go ahead and say omega dt is equal to d theta. Okay. And we are going to integrate both sides. Now, also with the integrating, we're going to plug in omega from what we just found in the previous equation, okay, or the previous equation that we just solved for. So we'll have some theta, should say d theta from theta I to theta, okay, is going to equal the integral of, and it'll be omega final equals omega naught plus alpha t. Okay, so we're going to plug this in as omega here. So omega naught plus alpha t dt. Okay, so this will be from ti to t, and then we'll take t sub I to 0. Okay, so we should get now, we'll have theta from theta I to theta equal to omega naught t plus alpha over 2t squared, and that is going to be from t sub I to t. Okay, so then we will have theta minus theta I, or theta final minus theta initial, whichever way you want to look at it. I know I'm kind of mixing up subscripts. That's kind of messing with me too. And then we'll have, we're going to say that this is going to go to 0, so then those two will go away. And so then we'll just have omega naught t plus 1/2 alpha t squared. Okay, and then we'll solve for theta here. And so we'll get this final expression. Theta final is equal to theta naught plus omega naught t plus 1/2 alpha t squared. Okay, and again, notice how similar this is to Cartesian coordinates. Okay, now let's find an equation that's independent of time. So we're going to plug that first equation into the second equation now. So our second equation is theta, I'm just going to say theta, same thing as theta f, okay, is equal to theta naught plus omega naught, and we're going to plug in a t. So from our first equation, we have omega equal omega naught plus alpha t. So omega is equal to omega naught plus alpha t. And we're going to solve for t. So we should get omega minus omega naught. Okay, put that over there. And then divided by alpha. Okay. So we will plug in our t here. We have omega minus omega naught over alpha. Okay, plus 1/2 alpha times omega minus omega naught over alpha, and this is going to be squared. Okay, let's see. Now we will have theta equals theta naught plus, and I'm going to go ahead and, what am I going to do? I do need to write all of this out, so bear with me while I do some algebra. Omega naught squared over alpha plus 1/2. One of these alphas will cancel, and then I have omega minus omega naught times omega minus omega naught. squaring that out. So I'll have omega squared minus 2 omega naught plus omega naught squared, and this is all over alpha. Okay, so now we should be able to cancel some stuff out. The omega naught over alpha will cancel, so this guy and this guy will cancel. And then I think that is it. So we have alpha equals alpha, I'm sorry, theta equals theta naught, plus, I'm going to go ahead with the 1/2 omega squared over alpha. Okay, and then I'll have minus minus 1/2 omega naught squared over alpha. Yes, okay. And so we can solve for omega squared. Don't have any room left. Did not plan this well. Okay, these can be pulled out, the 1/2 alphas from these guys. So I'm going to say delta theta. I'm going to call this delta theta because I'm going to move that over. So theta minus theta naught will be delta theta. Okay. And then multiply that by 2 alpha. Okay. Add over my omega naught squared. And if I'm doing this too fast, I totally understand. You can take out a piece of paper and write this over, because this is quite a bit of little tiny algebra that I just did in my head. So bear with me on that. And so, yes, I did find the correct equation. I have my final angular velocity equal to my initial and angular velocity, and those are squared, plus 2 alpha delta theta. Okay? All right. So, as you now can see, we have found our kinematic equations for our rotational motion, and this table is in your textbook, table 10.1, and it shows you what each of these are. Okay, so for this first one, it says that it's the angular displacement from average angular velocity, and so forth. Okay, so, excuse me. These are now our kinematic equations for rotational motion. So we'll be using these in our first example here, 10.4. Okay. It states that a deep sea fisherman hooks a big fish that swims away from the boat, pulling the fishing line from his reel. The whole system is initially at rest, and the fishing line unwinds from the reel at a radius of 4.5 centimeters from its axis of rotation. The reel is given an angular acceleration of 110 radians per second for 2 seconds. Okay. The first question is, what is the final angular velocity of the reel after 2 seconds? So we have our final, or our angular acceleration, and some radius. Okay, so we have r is equal to 4.5 centimeters. We have some alpha, 110 radians per second squared, and we have some time equals 2 seconds. We also know that our initial velocity system is at rest. We can say v naught or omega naught is equal to 0. Okay. I would probably just write the omega naught since we are looking at rotational motion. Okay, so we want to know our final angular velocity. We want to know omega. Omega. Okay, So let's figure out what we can use to find this. So we have some alpha. Let's see. We have an alpha, we have a time, and we have an omega naught. Remember, that is 0. So let's go ahead and use this equation. So we have omega is equal to omega naught plus alpha t. Okay. So that's going to be 0 meters per second plus, I don't know why I did that, plus alpha, which is 110 radians per second squared, times our time, which is going to be 2 seconds. Okay, so then I'll plug that into my calculator. I guess I could have done that in my head. Sorry about that. 220 radians per second is going to be your final angular velocity. Okay. Okay, now we want to know how many revolutions does the reel make. So how many times is there a rotation? Okay, and that is going to be swept out over some angle, right? So let's look at our equations. Okay, so we have some sort of angle that we want to know, some final angle, and we have our initial angle, that'll just be 0, we claim that, okay? We don't have an average angular velocity, so we can't use this one, but we do have our final velocity, right? We have our final angular velocity, we also have our initial that we solved for, and we have our time. So I would say we could use this equation here, okay, in order to find that final angle. So we're going to use theta equals theta naught plus omega naught t plus 1/2 alpha t squared. Okay, so again, our theta naught we're going to claim is 0. Okay, then our omega naught we found was 0. Well, it was given to us, okay, because it was initially at rest. And so now all we have to do is plug in our alpha and t. So we'll have 1/2 times alpha, which is 110 radians per second squared, times our time, which is 2 seconds, and square that. So now we can plug that into our calculator. We have 0.5 times 110 times 2 squared, and we get 220 radians that we sweep out. Okay, but we're asked how many revolutions, not how many radians. So remember that 1 revolution is equal to 2 pi radians. Okay, so 1 revolution in a circle, right? That'll be 2 pi radians, and that is also 1 revolution. So I can go ahead and use that to find out how many revolutions this is. Okay, so I have 220, divide that by 2 pi, and I get 35 revolutions. Okay, that's how many revolutions that reel makes. All right, let's get started on the next problem, 10.5. Now the fisherman applies a brake to stop spinning the reel. Okay, achieving an angular acceleration of -300 radians per second squared. How long does it take the reel to come to a stop? So we want to know some time. We have alpha, we have our final angular velocity and our initial angular velocity. So I would say we would use this equation here. Okay. And then solve for t, and we will do that in our next video.